All right, good afternoon. I'm John Rakovan from Miami University in Oxford, Ohio, and this next session is about a single mineral or mineral family, and that is apatite. The intersection of mineralogy with materials, biological, environmental, and earth sciences is beautifully exemplified by the wide range of applications and significance of apatite and apatite group minerals. And when we come to the discussion section, obviously there'll be time to ask questions of the speakers, but I would also like to come back, if we have time, to talking about this in general, not about apatite specifically, but there are many other examples of this. As scientists and teachers, having an arsenal of examples of interesting applications of minerals is something that we should all be carrying with us. And what I would like to do is ask the audience for new and interesting examples of where minerals are being applied in all areas of science and society. And the plan is actually to make a list and have something available on the MSA website for those of you who want to access something like that. And so before we start, before I introduce the speakers, we actually brought some teaching materials. Because the time at the end of the session is short, I'd like to pass them out now and then start the talks. And we have 3 baskets of fish scales, and these are from a fish called a alligator gar. If you've ever seen one, you know how scary it looks. But they're phosphatic. They're basically apatite. We also have something that Joe Pasteris will talk about in a little more detail, but I'll just mention this. This is a prosthetic eyeball. It was made from coral, calcium carbonate, but was replaced by apatite. And what's amazing about this is because it's apatite, and when it's put into the ocular cavity, it's recognized by the body, and muscle will grow into it, and it will eventually track with your good eye. I think it's just an amazing example of the types of things that are happening today in biomaterials.
Good afternoon. I'm pleased to be able to continue talking about the importance of apatite to society, now focusing on biological uses of apatite through apatite biomineralization and biomaterials apatite in the human body. I'd first like to thank quite a number of people. First of all, the organizers of this terrific symposium, Peter and Steve and their colleagues. I'd also like to thank my long-term apatite collaborators, Claude Yoder, Brigitte Vopenka, and John Freeman, and quite a number of bone collaborators, particularly focusing on Alex Demier, whose work I'll refer to in my talk show. So, the bottom line of this talk, apatite is biologically essential for real people like field geologists, geochemists, and just ordinary folks. So my approach today will be to take a look at the properties of apatite. Our interests in those properties differ according to the use of the apatite. And so we've already been introduced by John to the mineralogical outlook on apatite. I'll concentrate more on medical issues, so biological apatite. Whoops, got the wrong. There we go, sorry. Biological apatite, bones and teeth, and biomaterials, which are synthetic stand-ins for our own body's organs, including hard parts that are defective in some way or even missing. So mineralogically, we're familiar with thinking about the hardness, the density, the solubility properties of a mineral. But here, as we begin to think more biologically, we'll be thinking about such mineral properties as stiffness, surface properties, surface energy, crystallite size, crystallite shape, and the degree of crystallinity of the material. So, bioapatites. What is bioapatite? I'll begin by telling you what it is not. It is not hydroxyl apatite, and please don't ever let anybody try to tell you that it is, and I hope you'll be convinced by the end. So we have one kind of bioapatite in bone, 2 different kinds of apatite in tooth material, enamel and dentin, brachiopod shells of a particular genus, the hard parts of conodonts, the gar fish scales that were passed around. And then we have some not so nice unwanted calcifications, kidney stones, salivary stones, breast calcifications, heart calcifications. Some of you may think about fossil tooth and bone. Actually, although they began life as bioapatite, they have been replaced by a different composition of apatite during the fossilization. So apatite offers its chemical and biomechanical properties to these various uses. So for instance, with respect to bone material, get this right yet, won't I? The reservoir of calcium and phosphorus that is in the bone material is incredibly important, and there is so much substitution of carbonate for phosphate in bioapatite that the carbonate to phosphate ratio in the biological apatite actually acts as a pH buffer for our body fluid. Biomechanical properties, think of your own skeleton. It supports you, it protects your internal organs, it offers you locomotion. What are we thinking in addition here? We're thinking about mineral solubility. We're thinking about how this mineral responds to those motions. And so we end up having to consider here these two kinds of bone cells, the osteoclasts that are dissolving bone away, the osteoblasts that put new bone down. What is this response that's going on? Well, it's in response to our motion. You have a bone, you have a muscle attached to that bone, you're using it a lot. Over time, that bone will thicken. You get laid up in bed for 6 months and don't move much, and you will find that the bone thins. And these are the two sets of cells that are taking care of that, the removal and replacement of the bone. Biomechanically, we'll also be thinking about the crystallite size, shape, and surface area. And as you perhaps have marveled sometimes about how bone has this great stiffness and strength while still maintaining flexibility, you actually were reflecting on the properties of the apatite mineral. So let's first take a look at apatite in bone, sort of a cartoon here representing the hierarchical structure of the bone from this nanoscale down to the macro scale. And the heart of it, at least to us mineralogists, are these nanocrystals of biological apatite. Just a couple of nanometers thick, just a few tens of nanometers in the other two directions. They don't do it all alone. They are in a nanocomposite consisting of the nanocrystals and then these nanofibers of collagen. But what is really giving the remarkable strength, properties to the bone is the fact that these two very disparate materials are intimately intergrown with each other and interfaced with each other. And so the surface properties of the bioapatite become incredibly important in that strength and stiffness of the bone. The bone itself and the bioapatite, as I just indicated, biologically, biochemically, and mechanically responsive. This is quite remarkable. You take a look at the sort of time frame in which bone, including the bone apatite, can grow. How is this even possible to have this sort of change in amount of bioapatite? Well, part of it has to do with the fact that it's quite soluble and can be removed easily. That solubility is due to the 3 to 8 weight% carbonate that's substituted into the bioapatite. And note, hydroxyl apatite is not what any chemist would call soluble. This is a very different material. And so the bioapatite has this rapid response time and becomes involved in growth, repair, and remodeling of the bone over time. Let's take a look at the tooth. You see we have two types of bioapatite here, the enamel and the dentin, very different properties. So the enamel is hard, not soluble. This is good. It doesn't have collagen in it. In contrast, the dentin, much more bone-like, elastic. I perceive it to be a sort of mechanical buffer against the shock of mastication as you're chewing. So what is the difference between these two kinds of apatites that sit side by side here? It's mostly the carbonate substitution. And so enamel has only about half the carbonate that the dentin has, and that gives the big difference in properties, including things like solubility, hardness, and actually the fact that the dentin crystals are considerably larger than the enamel crystals are considerably larger than the dentin ones. So I've told you what bioapatite is not. What is it? Well, I said it wasn't hydroxyl apatite. So let's begin here with this hydroxyl apatite structural diagram to show you that bioapatite is indeed a spin-off of hydroxyl apatite. Talking about this 3 to 8 weight% carbonate substitution, A-type substitution of carbonate for hydroxyl in the anion channels here, and B-type carbonate substitution for phosphate, replacing the phosphate tetrahedra. And so if you put that in the form of a formula, the pure A-type substitution would be represented like this. The pure B-type, considerably more complex, represented by that formulation. Well, of course, the bone apatite is not grown in a beaker. It's grown from the body fluid. So we want to see, for the real bioapatite, what are the other components to think about besides carbonate? Hydrogen phosphate, sodium, magnesium, and potassium ions. And it's a good thing they're there, frankly, because we have to fulfill charge balance here. And some of you may have noticed we didn't do that very well up here. We have a 2- substituting for a 1-, but that actually can be handled very easily. Then we have a 2- substituting for a 3-, and that gets to be a little bit more difficult. And so we find out that what actually goes on in this B-type substitution, which for decades was thought to be the dominant form of substitution in biological apatite, but that's been called into question recently. We see we have a coupled substitution, sodium coming in with the carbonate. We still have some vacancies left, and I don't want to forget several weight% water that also is part of the biological apatite. So no, it is not hydroxyl apatite. What is it that's going on here that gives control over this bioapatite because of the carbonate substitution? This is the goal of a multidisciplinary study that I was part of that was headed up by my colleague Alix Demier. We looked at the apatite in various kinds of ways. We had aqueously produced apatite at 60 to 80 degrees centigrade, no organic molecules involved at all, so totally inorganic. And so we're looking over here at transmission electron micrographs by Alix Demier of these apatites. And so you'll note the carbonate increases from 1.6 to 2.8 to over 17 weight% carbonate substitution, and it's still an apatite, okay? And so what accompanied that increase is a decrease in the crystallite size, an increase in the degree of aggregation, and a change in the shape. No longer our nice hexagonal prisms of apatite, but rather first blades, and then further on we get into platelets. Then looking into the mechanical properties of the apatite as a function of carbonate substitution, our colleagues pursued this through theoretical calculations. They assumed that all of the carbonate was replacing phosphate, and so you have here an increase in elastic constant, and here we have an increase in the carbonate concentration. And so what you see here is this increase in carbonate lowers the resistance to elastic deformation. In other words, the stiffness decreases as the weight% of the carbonate rises. And then lastly, looking at the solubility, the KSP increasing in this direction, weight% carbonate again increasing in this direction, and we see for this range up to almost 18 weight% carbonate, we see an increase of 12 orders of magnitude in the solubility of the apatite. And in addition, when we did X-ray diffraction and Raman spectroscopy on those samples, we found that as the carbonate increased, the degree of crystallinity of the material decreased. So here we get to my non-geological analogy, if you will bear with me. I see apatite as a sort of multi-tool. And all of these little facilities poking out here represent, in my mind, the different kinds of sites in the apatite that allow it to accommodate ions of quite a range of sizes and shapes and also charges. But boy, the real winner here is the carbonate, whose amount of substitution controls the size, the shape, the degree of aggregation of the crystallites, the stiffness, the degree of crystallinity, and the solubility of the crystallites. So what single tool can you think of that can accomplish so many different things? Behold, the humble screwdriver. So to me, the carbonate is the screwdriver that tweaks those remarkable properties of the apatite. But it's not all good news. And so we look here, as John indicated, we have worries about breast cancer. And so we see here breast calcifications, which you know sometimes are associated with breast cancer. Interestingly, we have two different types of calcium-bearing minerals in breast calcifications, and with the one type, we have two somewhat different compositions that turn out to be important with reference to malignancy. So we have wetellite calcium oxalate dihydrate. It's a rare calcification associated with tissue that's benign. Then we get to our carbonated apatite over here, and for the higher carbonated apatites, as indicated here in this Raman spectrum of the tissue there, that tissue is benign with a higher carbonated apatite. But if we have a lower concentration of carbonate in the apatite calcification, then that's associated with malignancy. So unclear who's the driver, the cause and effect here, but an important tracer. I'll end then talking about biomaterials, and specifically biomaterials to substitute for hard parts. And so you might say, oh, hard parts, we need something that's strong and stiff. We're thinking about metals, right? No, because even in the context of strength and stiffness, apatite still wins out because it can claim to be biocompatible, bioresorbable by those same osteoclasts that remove bone. It's also osteoinductive, so it's actually encouraging new bone to form on top of it and throughout it. We find that when we do take a metal prosthetic, we find that it does really not very well next to healing bone until we have coated that piece of metal with hydroxyl apatite. And then lastly, the ability of these apatitic biomaterials to incorporate pharmaceuticals that can then be slowly released in the body. So these two images here are to try to give you some sense of the breadth and importance of these biomaterials. And so I'll own up, it's a big business. It's one of these multi-billion-dollar industries to make these sorts of biomaterials, but it's also, for many people, a new lease on life to have one of these substitutions. So over here, we see that we have the 31st Bioceramics Conference, and they give you suggested topics. And the first one here is calcium phosphate bioceramics. I've learned that ceramics is the term that materials scientists use for our minerals, but I'll let them get away with it. Then here we have a whole list of what can be replaced by what material. And yes, there's alumina and there's glasses, but look at all of the hydroxyl apatite shown there. These apatitic biomaterials are incredibly important. So let's take a look at some of these, and the numbers are the same in my list as on the various diagrams. And so we have dense, porous material that can be shaped, and so the ocular implant that John passed around, that would be of this type. We have hydroxyl apatite composites, which means composites with synthetic polymers or with natural collagen. We have apatite cements, absolutely marvelous. These so-called bone cements that are injected into fractures, for instance, in spinal vertebrae. The people who have it tell me the pain goes away immediately. We have amorphous calcium phosphate, which is an incredibly important, powerful material, both biologically and in biomaterials, and it needs its own talk, so I move along. The bioactive glasses may or may not have calcium and phosphate in them. Then we get to the apatitic coatings on metal implants, like this one here, and it's done through high temperature, greater than 1500 degrees, a plasma spraying process, little beads of melt that then crystallize into rather complex solids. And I'm sorry, Robert Hyman was not able to come today because I put this slide in here so I could show that Robert Hyman, a fellow mineralogist whose plane failed him as he tried to come, he is world-renowned for his work on the plasma spraying process for hydroxyl apatite. So ending up here, apatite and us, I guess we could call this. I thought, boy, we have lots of kinds of bonds here. We have chemical, mineralogical, and societal bonds, all with apatite. So inorganically, we have apatite as a source of phosphate fertilizer. Apatite also is a sink, a sequesterer of unwanted elements, including lead. And so here's a different version of lead apatite inside of this lead pipe to prevent lead poisoning. Then biologically, we've just heard about bones and teeth. They have specialized properties. These come from special compositions of biological apatite. The unwanted calcifications, but hey, maybe we can spin this into some sort of cancer monitor. And then, of course, biomaterials to replace tissues and organs. And here you see synthetic enamel being grown. So the three of us offer to you elements, a mineral for all seasons, and among those seasons is the summer picnicking season and the very newest apatite species, snapatite. Not yet recognized by the IMA, but sold on Amazon anyway. Thank you.